Okay, we are going to continue. So we have now a theorem 1 and a theorem 2. And recall that our aim was to describe all finitely generated modules over a principal ideal domain. And in the beginning I said that if you have such a module, you can surject an d to the n for some n, natural number n, to that module. So then we are going to get into this situation. And then now we are ready for the next theorem then. And this is the classification theorem. So it says let D be a principal ideal domain and M a finitely generated module over this D, so that is a D module. Okay. Then there exists an R and an S in the natural numbers, and there exists D1 up to DS in D with 0 removed, such that this M is isomorphic to D to the R, direct sum, and then I get D modulo the ideal generated by D1, D modulo the ideal generated by DS. That's the classification theorem. So it means that every finitely generated module over D module is actually a direct sum of modules generated by one element. And the first R of them are just free, right? And the others are quotients by non-zero ideals. And that's a very nice result that has no generalization to other rings that I know, right? Well, sometimes projective modules are free over very nice rings. That is, those are very difficult results. So let us, before we do a proof, we can make a remark. You can even get, so R is uniquely determined by M, and also, so S and the ideals generated by these things, if you ask that D1 is contained in D2, is contained, and so on, is contained in DS. If you ask the containment of these ideals, and you can always get that, then there is a lot of uniqueness about this. And these ideals have a name. They are either called invariant factors or elementary factors or something, right? That is, okay, that's one thing. And how do we prove this? Well, let me start the proof here of the theorem 3. So we choose a surjective morphism from D to the N to M, and we can do that because M is finitely generated. Then we have the following nice diagram. We have Dn has this surjective map to F to M, but we can also say, yeah, but we also have a quotient map to Dn modulo the kernel of F, right? That is, and by, well, what Arno has said in the previous lecture, such a quotient has a universal property. Any map from D to the N to some module that is 0 on this module, this submodule that we divide out, for example, this F is by definition 0 on the kernel of F, you get a factorization like this. But we divide out exactly by the kernel of F, so that means that this is injective, And because this is surjective, the image of f is everything, then the image here is also everything. This is an isomorphism, this thing. So now we understand this m a lot better because it is isomorphic to a quotient of d to the n by a submodule of d to the n. But there we can use theorem 2, right? So theorem 2 says that we can choose better bases. Oh, theorem 1 says actually that this kernel of f is free, right? That is what theorem 1 says. Here, it is still there, just before I erased it. Well, I will maybe erase it. Right? Theorem 1 says that kernel of f is kernel of f inside d to the n. This is free by theorem 1. And then theorem 2 says that I can take appropriate bases for dn and for the submodule kernel of f, right? So, so then by theorem 2, we take bases e1 up to en of dn, so not the standard basis, but a new basis, and say f1 up to f, how much? M, say, of the kernel of f, right? I mean, I can take those, so, and d1 up to dm in d with 0 removed, such that fi is di times ei for all I in 1 up to m. That's what theorem 2 gives me. But then I can say, well, then dn modulo kernel of f is d times e1 direct sum d times en modulo a submodule, which I write like this now because the board is not longer, d times d1 e1 plus, well, yeah, well, actually these are direct, they are in these direct summands, right? So here I have d1 e1, well, let me write d times that, direct sum d times dm em, and then n might be bigger than m, right? That is what happens here. I have to divide by this. And I claim that this quotient is the direct sum. So I'm going to compare it with this. D modulo d1 direct sum d modulo dm direct sum d to the n minus n, right? Because the last so many have no counterpart there. So I claim that this quotient is actually this. Well, how do I do that? I can first say, forget that we divide out by this. So I'm not going to erase it because then I have to go make it back again. But think for a moment that this is not here. Then I can make a map from here to here. Because I can just say that a linear combination of these things, this is free. On the first part, I just map it to this and 0 to the other map. Huh? So I just send, say, x1 e1 plus xn en, this thing here. I map it to x1 modulo this d1 up to xm modulo these, and then in the rest I do xm plus 1 up to xn. Right? I can do this map. And what is the kernel of that map? Well, that is exactly, when is this thing 0? Well, then x1 should be a multiple of d1. That is actually precisely when you are in here. So I claim that this map has precisely this submodule as kernel. And that's obvious if you look at what it is here. So then indeed, I get that now dividing this by this, it is isomorphic. And And I'm done, right? Because that's exactly what I wanted to have. M was isomorphic to this quotient, and this quotient is of that shape. Right? It is exactly here. So that's fine. End of proof. And now comes the really fun part. We can do 2 applications of this. To the structure of finitely generated abelian groups, and also to Jordan normal forms. There is nothing canonical about it, it's Jordan normal forms. Okay, so, oops. But maybe before we do that application, I would like to make a little thing here. So we have the Chinese remainder theorem, not for modules as Arno did, but just for rings, and now in the ring D. And it says that let D be in D, non-zero, and write it as a in its factorization into primes. D is a unit times P1 to the E1 times PR to the ER as before. Then D modulo D. Well, actually, I can give the proof while I write it. I look at the map from D to D modulo P1 to the E1 times D modulo PR to the ER as ideal. I look at this map. And, oh yeah, then you have to show that the kernel of this map is exactly this D, so this will factor through this, and that will be injective. And the usual argument, well, the GCD of these things, they are different prime ideals. And so the GCDs are 1, pairwise, and that means that this is surjective. So the Chinese remainder theorem tells you a bit more. It says that each such summand in this direct sum can be even decomposed a bit further into prime powers. And that's what I would like to write. So, okay, given that, I can do the application to finitely generated groups. Theorem. Let D, so I take here D as Z, right? So what is a Z module? A Z module is an abelian group. So let A be a finitely generated abelian group. Then there exists R in N, there exists an S in N, there exist prime numbers, primes, distinct primes, P1, oh no, why do I say that? There exist primes. There is no reason for them to be distinct. Primes P1 up to ES, E1 up to ES in N greater 0, say, such that A is isomorphic to Z to the R times Z mod P1 to the E1Z times Z mod PS to the ES Z, right? So that is what every finitely generated abelian group looks like. Okay. Then, and actually, when I gave examples for morphisms, Hom sets, or Hom abelian groups in the category of abelian groups, I also told you what the Homs were between Z mod N and Z mod M. So you can, with that, you understand not only the objects, but also all the morphisms. So that's a very good thing. Now we take this, the polynomial ring in one variable over K, and we're going to suppose now that K is algebraically closed. K algebraically closed. If you want, you can think of the complex numbers. And then the primes of k of d, of kx, are up to units be x minus lambda, where lambda runs through all of k. The monic polynomials of degree 1. Because algebraically closed means every non-zero polynomial has a root, then you can factor out such a thing, and so in the end, every element can be factorized into products of these. So those are the roots. So actually, now we go back to something else that we discussed. Let V be a finite dimensional K vector space, and A from V to V, K linear. So K is an endomorphism. Then we have seen that we can make, then V is a Kx module where X acts as A. And I would like to find a very nice basis for V such that A has a very nice matrix with respect to that basis. And how does that work? Well, you use this theorem, because the theorem says, theorem 3, that V as a Kx module is isomorphic to Kx to the R direct sum Kx modulo x minus lambda 1 to the E1 direct sum direct sum Kx modulo x minus lambda s to the Es, right? And so if we can find here a basis for which the multiplication by x has a very nice matrix, then we have here, and we map that through an isomorphism here to a basis here, then that basis, with respect to that basis, A gets the same matrix. So we can look at what happens here. Well, maybe first I should say, what about this R? Because this is a finite dimensional vector space, but R, Kx itself is infinite dimensional, so this can only happen if R is 0, right? So we can forget about this, and we only have these things. And so now, let me do it on this blackboard. We can look at each direct summand separately. That means that we will get, anyway, a kind of block form for our matrix, indexed by these numbers 1 up to S. So I only have to think about one of these things. So if I look at this, Kx modulo x minus lambda to the E as a Kx module, I would like to take a nice basis of this, right? This has a K basis, 1 x minus lambda up to x minus lambda to the E minus 1, right? That is the basis I would like to take. This is a K basis because division with remainder by this polynomial shows that every element here has a unique representative that has degree less than E. And that means it is a linear combination of these things. Right? So that is a basis. And with respect to this basis, the multiplication by x minus lambda, so this is the multiplication on this, has the matrix. Well, 1 under multiplication by x minus lambda goes to the next. So the first column is 0, 1, and then zeros. The next column is 0, 0, 1, and then zeros again. So these ones go down up all the way here, and here I have zeros, right? And all here I have everywhere zeros, except ones just below the diagonal. But then it means that the x is x minus lambda plus lambda, right? And so the matrix of multiplication by x is the matrix of this plus the matrix of multiplication by lambda. So the matrix of x dot has matrix the one that you are familiar with, lambdas on the diagonal, ones below the diagonal, and then zeros everywhere else. And that is a proof that over an algebraically closed field, every endomorphism of a finite dimensional vector space can be brought into, well, block form with these blocks, right? That is because each of these terms will give one such block. And that's the end of the course, I think, for today.